Hello, and welcome to Teledyne Labs webinar, Best Practices for Using Carbon Dioxide to Gain Better SFC Results. Today, we are lucky to be joined by Eric Seast. He is newer to the Teledyne family, and we're really happy that he can share this information with us. Before we get started, I would like to remind you of a few things. If you happen to experience any video or audio issue during the webinar, please leave and rejoin. This typically clears up those issues. This webinar is being recorded, and the video along with the slides will be made available to you in the near future. So with that, I would like to welcome Eric.
Thanks, Sharon, and welcome everybody to this webinar. I'm Eric Seast, and I've been involved with the use of carbon dioxide and SFC chromatography since the late 1990s. So I hope to spend some time here talking through the whole topic of carbon dioxide and giving you an overview of what that is and how it's applied to today's supercritical fluid chromatography. First of all, let's start with a discussion about the properties of carbon dioxide. As you can see on the slide, at ambient temperature and pressure, which are the conditions we're living under, it's a colorless and odorless gas. Now, if you modify temperature and pressure, you'll see from the phase diagram in the bottom left of the slide, the various physical states that carbon dioxide can be in. For example, when it's a solid, we often know that as dry ice, but that's at very low temperature, minus 78.5 degrees Celsius. It can also be in liquid form, so a little bit warmer to achieve that. And then also it can be in what's termed supercritical fluid form, and that's the box up in the upper right top corner of that phase diagram. So physically, when you're doing this on using CO2 in an instrument and you're increasing your temperature and pressure, in this case, we'd be starting with the liquid that's in a container of CO2. There'll be some gas present, but as you increase the pressure and temperature and drive the phase change toward the supercritical fluid, this picture of the phase changes goes from left to right, and in supercritical state, you have one phase. So first of all, where does carbon dioxide come from? Obviously, there's natural origins to it. It's in our atmosphere that we live in, and it comes from a lot of processes. A big one being it's a respiration product from living things. So we are as humans breathing out CO2 in our breath, and we're obviously, when we breathe in, we're trying to breathe in oxygen, and then our body converts that during respiration. The decay process with dead things also releases carbon dioxide in the atmosphere, and then also with emissions from combustion like wildfires, volcanic eruptions, all that also CO2 is a byproduct of combustion. And you also get outgassing from organic matter that's contained in the oceans, which is obviously the biggest part of our planet. Human origins, we also can contribute to this, and our main contribution is through the emissions from combustion, using fossil fuels like coal, natural gas, and oil, like the past couple of centuries especially. This, of course, has become an issue as time has progressed. We have concerns about global warming, the temperature in the world increasing, so that's in the news. Obviously, we're releasing CO2, as mentioned earlier, into the atmosphere with a lot of our industry. And then concern too is how that affects climate in this world. There's also a lot of research being done on how to capture carbon and reutilize it and store it. and that's ongoing as well. So when we think further about carbon dioxide and how it's used in everyday life, it's obviously essential for life. The photosynthesis diagram shows you how, again, plants, they like carbon dioxide, and they obviously release oxygen into the air, which obviously helps aid life and helps us live together on this planet. It's also utilized for food preservation, carbonation of drinks. I think we all like a soda once in a while. Fire suppression, it can be used for that. And medical applications, it's often used for things like laparoscopy, as an example. It's also can be used as a refrigerant, and actually was fairly common a century ago with that type of usage before newer refrigerants came along that were more efficient. It's also been used for extraction purposes for many years, a few decades for sure, to extract things like caffeine from coffee, or it's been utilized to extract components from CBD and THC from cannabis. And finally, the main purpose of this talk is to show how carbon dioxide is utilized by a technique called supercritical fluid chromatography. So let's jump into the topic of supercritical fluid chromatography, or SFC for short. It was first described by Klesper back in 1962, and it was given a different name at that time, and it was really being viewed more as a gas chromatography technique under high pressure. And then that term was actually coined just before the invention of the term HPLC, which I think many of you online are familiar with already. So commercially viable prep chromatography equipment for SFC didn't really come along until the 1990s. And I'm using the example of the Berger equipment shown in the pictures, which really helped provide reliable equipment that could be used in a modern day laboratory. And those are instruments that I also learned how to do prep chromatography on in the late 90s, early 2000s. Finally, it's become synonymous, SFC has, with novel LC, it's a novel LC-like technique that utilizes packed columns, much like HPLC. So in the next slide, we compare the liquid chromatography approaches like HPLC and flash, which are things we all use in our laboratories and have been used since the 1960s. There's obviously been improvements in instrumentation since that time. The term normal phase has been coined back at that time. This is where we're typically using non-polar organic solvents, generally alkanes like heptane, in combination with a more polar solvent to help elute samples from, most cases, silica gel, although there's other media that can be used in normal phase mode. Reverse phase mode has also become popular, and it's called reverse phase because it's kind of the opposite of normal phase in the sense of how the solvents are used. In this case, you got a non-polar stationary phase like C18, which is probably the most commonly used reverse phase stationary phase, and you're using polar solvents like water and mixing those with less polar solvents like acetonitrile or methanol to do chromatography. Generally, these techniques are then utilized either in flash mode, which generally implies the use of larger particle size media. Back in my day when I started in this field in the late 80s and 1990s, we called it HPLC when we were using large particle, but modern day flash equipment does that all very well. And those instruments are much more compact, and all of our chemists use those this day and age. So instruments like the Combi Flash Next Gen series, or you might be familiar with our ISCO RF Plus or our RF series instruments from previous years. HPLC, these are high pressure systems that can go much higher pressure than the typical flash instrument. And in the case of our AccuPrep HP150, you can run the system at up to 6,000 PSI system pressure. And we're generally using smaller particle phase media, less 10 micron or less particle size for that. And those can be used either normal phase or reverse phase. And those are what we term more traditional techniques that every lab is using in this day and age to purify molecules. So let's think again about CO2. If we were to use it as a solvent and use it in this SFC mode, why is it, what makes it attractive as a mobile phase solvent? There's fortunately a lot of great features about carbon dioxide that make it a great solvent. It's chemically inert and stable. It's readily available and inexpensive. It's renewable, commercially available. When the CO2 that you buy from a gas supplier, we're basically reusing CO2 that was generated from some other process. So that's why we refer to it as more of a renewable or green source. Even though we obviously don't want to pump more CO2 in the atmosphere, we're reusing what's already there. It's non-flammable, non-toxic, which are great if you're running chromatography all day. You don't want to be exposed to some of the nasty solvents that we get with standard normal phase or reverse phase flash or HPLC. One of the downsides is it is an asphyxiant by displacing air that we breathe, so you do have to use ventilation. It is mildly acidic and corrosive, and however we can turn the acidity into an advantage, and that actually is beneficial for use with some of the types of either acidic molecules that we're trying to purify. You may not need to use a modifier, and we'll go into more detail later. So it is miscible in water as well as all the organic solvents, which is a great feature, so we don't have to worry about, we can use the spectrum of solvents available commercially. When it is compressed into liquid or even higher pressure and temperature and SCF form, it has similar allotropic solvent strength to that of alkane. So it behaves pretty much like heptane or hexanes, except that it is mildly acidic. So it's more normal phase like, let's say, the way it's used. It also has very low viscosity, which also gives it the ability to penetrate the pores on your solvent, on your chromatography media, and give you much higher resolution on the same type of column you might be running in HPLC mode. So, and we'll talk more about that as well. So some terminology that gets thrown around between LC and SFC. So when we talk about solvent and SFC, we're often referring to the carbon dioxide. In LC, the comparable term would be the weak solvent, generally speaking, so like heptane. When we talk about modifier or co-solvent in SFC, we're generally referring to the more polar solvent that's added and mixed with the CO2 on the instrument. And that would be comparable to the use of the word strong solvent or something like ethyl acetate in LC. So generally, because we're already using the term modifier or co-solvent for the second binary solvent, we'll often use the word additive if we're going to spike in some type of compound like an acid or a base or a buffer or even water to help improve the separation. In LC, that's generally just referred to as a modifier, so we don't want to confuse those terms. As already mentioned, it has the allotropic strength of hydrocarbons, which is great. And generally speaking, we tend to do SFC with alcohols, methanol and ethanol being readily available. However, you can use IPA, acetonitrile, ethyl acetate, even methylene chloride, although we're trying to not use that so much anymore in our chromatography as more and more restrictions on its use due to toxicity. And generally, you want your analyte, your solvent you want your sample to be readily soluble in that co-solvent. So that often affects the choice too, but you also have to get separation or selectivity on whatever stationary phase you're using when you're doing your analytical screening. Again, water is just mainly an additive. You can buy it in 5% amounts in alcohol already, depending on how the alcohol is distilled and commercially. And adding water in can add some advantages, especially if you're using something like silica gel as your stationary phase. And you can even use larger amounts and use small amounts of CO2 and sort of run a technique that's mostly polar called EFLC for more polar molecules. And common additives that we all know from regular chromatography, acetic acid, TFA, ammonium acetate, all these same types of modifiers we use in HPLC can be used with SFC as well to either improve peak shape or help with elution from a given column or stationary phase. And you can also, it may actually be a requirement to use it. So depending on the compound class you're doing chromatography with, may dictate how you start your screening and method development. So again, instrument-wise, SFC looks very much like LC. You can see our AccuPrep SFC was designed to be a very compact system, much like our HPLC to the right. It's scalable just like LC from analytical to prep. I mean, and I like to oversimplify it by basically saying you're doing HPLC with carbon dioxide as a solvent, although there's a little more baked into the engineering on the instrument. So because CO2 is compressible, something called a back pressure regulator is required to keep the system pressure from the inlet side of the system all the way through the outlet side of the system constant. You can also modify pressure, which gives you another parameter perhaps for optimizing your chromatography. Generally speaking, it's the last parameter in practice that we mess with, but sometimes it can be helpful for improving the peak shape of your later eluting peak, for example. Temperature control is also a requirement, especially on the front end when you're bringing the carbon dioxide into the CO2 pump heads. You've got to keep those pump heads cool because they'll generate heat as you're pumping the CO2. Generally, we like to heat the column itself, and on the AccuPrep SFC, that's done with a column oven, that middle module in the picture shown, which also has a column selector for up to 6 prep columns. Finally, one has to use a gas liquid separator to separate, depressurize, and remove the CO2 at the end of the process before collecting fractions in your co-solvent in this case, and do that in a controlled manner. So you want your pressure to be almost near zero when you go to collect sample in your tubes or bottles on your fraction collection side. So the GLS is something we'll talk a little bit more about as well. On the AccuPrep SFC instrument, it's up on the top module on the right side. Barely see that, but so more commentary about chromatography, why we use SFC. You can use it for chiral application. It's orthogonal to both reverse phase and normal phase. In fact, it bridges both very nicely and could actually be used for, instead of both techniques for most small molecules out there. And for even some of the larger molecules, it's being looked at further. It's very efficient, as I mentioned, because of that low viscosity and the way it solvates the stationary phase. You can run at much higher flow rates than with other organic solvents or even water, 3 3 to 5 times faster, which is great, especially for chiral chromatography, which is historically very slow technique. It took hours sometimes to develop methods. Now you can develop methods in minutes and do prep work in minutes instead of half-hour time increments. So much faster processing time, equilibrates much faster because you can run at the higher flows, and then you end up with more concentrated fractions that are generally just in an organic solvent, so easy to evaporate, and smaller volume. We already talked about greenness earlier. We're CO2 neutral in the way we're utilizing this, and all you have to do is ventilate the CO2 safely so that the user is fine. So again, it's you don't have to store the organic solvent waste or as much of it due to the process, depending on what your percent co-solvent is in your system. So you are saving solvent over traditional chromatography, and it's because it's non-toxic, you can also use it safely for food and pharmaceutical product work. So, number of application areas. I'm not going to go into detail other than we mentioned natural products earlier. Pharmaceuticals, it's applicable to some biologics work as well. Food and flavor industry uses it heavily for extraction especially, but also chromatography. Agrochemicals and the fine chemicals industry. So why is it not utilized as much as it could be in today's modern laboratory? Well, even if you go back several decades, a lot of the earlier systems had, you've got the challenge of how do I get CO2 to my system? So that caused some people to shy away from using it. And we know more about how to do that better this day and age, so not as much of a barrier now. A lot of the applications that I referred to earlier were kind of developed over the last couple decades, so it's improved. We know more about it now, and therefore that's not as much of a barrier in this day and age. The hardware's used to be quite complicated. Now you can pack it into a box like the size of our system at the bottom there. Poor sample recovery used to be a problem, but now we can do very controlled fraction collection into the vessels. So that's not an obstacle anymore. It used to be challenging to interface the systems. That's much better as well now. Used to be you had to be an expert user. Now I would say with our system, with just a little bit of training, a chemist who's not familiar with the technique can learn it within a few hours and be off to the races doing prep chromatography with it. System reliability is much better now, and I already mentioned footprint. You can see the footprints have been shrinking over the years, especially with our current system. So yes, we can do more in less space with our system. It has a very good pumping system as well. It has unique technology designed to help pump CO2 effectively in a very controlled manner throughout the instrument, and nice software interface that a lot of our chemists are already familiar with if they've used our flash equipment or HPLC equipment. So the SFC system itself it's very versatile. You can collect in bottles like shown on the left. This is often used for simpler mixtures and for if you're doing larger scale work and want to collect gram amounts of material. You would often collect the fractions in this manner, and you'd most likely run either some sort of isocratic run to separate the components into those bottles. There's up to 8 positions available. Although if you add an auto sampler like you see on the right, one of those 8 positions is used to feed into the auto sampler. And you can run either mode and collect in open tubes like shown on the right. So we refer to those techniques as bulk purification with bottles versus multi-sample. There's also multiple detectors available, so you can use evaporative light scattering if you have non-UV chromophoric samples. And that detector is built right into the top module near where the UV detector is built into the system. You can also add a mass spec unit next to this system if you want to monitor or collect fractions by mass. That's often popular with the multi-sample purification approach that a lot of people use using reverse phase in the field. And in this case, if you're wanting to run gradients with samples that have a wide range of non-polar to polar components in it, you can run gradients on our system anywhere from 5% co-solvent up to 70%, which is a higher coverage than some of the commercial prep systems out there today. We also have an ability to run sort of an analytical screen on our columns, on the prep columns in that system. So you can, if you put 6 prep columns in there, you could run a tiny amount of material on each and get answers quickly on which stationary phase might be best for your sample, and not use an analytical instrument. And you'd only utilize maybe 1 milligram or 2 of sample, depending on how you do it, and assuming you can, the detection, you can, there's electronic ways to increase the signal to noise for doing that. Then you can go right to, you take that scout information, and you can go right to what we call a focus gradient algorithm and generate your method quickly. I won't show that in this talk, but we have other documents that we can show to you if you'd be interested in learning more about that algorithm and how to get prep conditions quickly without having to be a prep chromatography expert to come up with ideal conditions for scale. So how's the CO2 liquid pumped? User sets a flow rate in the software. The pumps will work as if they're pumping the usual liquids like an HPLC. Because liquid CO2 is, for lack of a better word, it's squishier than a lot of other liquids, more compressible. The real delivered flow can vary drastically. However, our system will give you what we term a real CO2 flow. Again, you set the flow rate, pumps will start working like so. And we use what's termed a mass flow controller in the instrument that actually measures the real flow and helps the BPR and GLS and the rest of the components in the system adjust. And they all talk to each other electronically. And therefore you get a very steady, smooth CO2 flow with our pumping system. And it's constantly adjusting to maintain that flow rate. So that works very well on this instrument. I've used a lot of different types of instruments over the years, and this one's fantastic in that regard. This is a flow diagram of the instrument. I know it's a little busy, but the green flow path is basically your CO2 flow path into the system. I'm not going to describe every component that's here, but I'll say, I mentioned you need to cool your pump head, so you got a chiller or booster pump feeding in from your CO2 supply, and I'll go into more detail on subsequent slides on that. You've got the pressure transducer measuring actual pressure, and you've got your pump, your mass flow meter. That all feeds into the instrument. In the meantime, you've got this separate pump flow using the co-solvent in yellow. Goes through the valving that's shown here, and then your sample is injected into that flow here, kind of in the middle of the diagram in yellow. And that's then mixed with the CO2 and goes through one of your 6 columns that you might have plumbed through the red path, as your material moves through the column and separates. On the back side of the instrument, like I described earlier, the BPR adjusts that pressure and maintains it. In general terms, we usually start with, say, 100 bar setting on the back pressure regulator to maintain the pressure. And then on the back side is where the GLS resides, and that's where we vent the CO2 to the exhaust system, and we collect our fractions in the co-solvent. So types of CO2 available. Obviously, you can't go to your closet and pull out a 4-liter bottle of liquid CO2. So commercially, you can buy these higher pressure cylinders shown at the top. They're smaller volume generally, and depending on how much SFC you want to do, you may likely have several of those in your laboratory adjacent to where your instrument is set. And so you can also get larger dewar type containers that contain more of the product, and we'll go into more detail on those. And you could also, like you might use in the building that your laboratories are in, you can use bulk tanks outside the building and pipe CO2 into your building and laboratory, much like is already done with commercial gases like nitrogen and so forth. So if you have the cylinder approach, as mentioned, you can connect these in series and feed the CO2 into your instrument like shown to the right. Cylinder pressures generally anywhere from 800 to as high as 1300 psi. One can use a warming jacket around the cylinder, because when you do pull the CO2 out, it's going to drop the temperature in the cylinder and make it frost up a bit. So if you want to help maintain that pressure, heating it is very useful. You can use a CO2 bath near the, or a cooling bath, I should say, for the pump heads. I already mentioned that, keep the CO2 pump heads cold. Cylinder pressure reads significant pressure though, even when the cylinder is nearly empty. So you'll still want to have several available just in case. And our instrument's designed, if you do run out of CO2, it'll automatically stop when it feels the pressure drop. And you can often connect up another tank within a few minutes and restart and not affect your chromatography very much. That's a nice feature with our instrument. May not be perfect like the previous run, but you at least don't lose material or have to flush it off necessarily. One way to track the levels too, you can use floor balances because there's tare weights stamped on each cylinder. That's another way to monitor how much CO2 product's left in these, because you can't see inside otherwise. You're totally reliant on the regulator and the weight. Now these have to be transported, so we'll go into, they have to be strapped down to whatever cart you're using to move the cylinders around in the lab and to your loading dock for either removal or for bringing up to your lab. So they should be also strapped to the wall when in use. You don't want them falling over. If you know you're going to do a lot of SFC, you may want to use larger containers like these dewars. These dewars are generally, they are insulated, and the pressure regulation works very nice on those. However, the pressure is lower, so we have to use what's termed a booster pump to increase that pressure from sort of the typical, let's say 358 psi, and boost it up to say the 1000 psi needed at the instrument. These can also be connected in series if you want to use that approach and don't have the money for a large bulk tank outside the building. A lot of the other features or things described for cylinder use are also noted here. Because the dewar pressure regulator is much more accurate, and most modern dewars also have sort of a built-in CO2 level sensing ability. You are able to get a better idea on the levels of your CO2 in each dewar as you're using them. Sometimes you have to add heat back into the dewars when they get cold in this case, and there's some controls on the top of the dewar system that allow you to copper coil that you can open a valve on to allow ambient heating going to back into the very cold dewar. Because these generally have built-in wheels, they're much easier to handle, although they're very heavy. But you can roll them into place wherever your booster pump delivery system is going to be staged. Bulk CO2, again, pressure is even lower on a big tank, as you'd imagine. So you can bring your carbon dioxide into your building either as a gas, which is often preferred for transport throughout a building. So around 100 psi generally for that. If you do want it to be in liquid form, you can increase the pressure to around 200 psi and push it through your building in that manner. But unless your lab's adjacent to the source, that's often, from a safety standpoint, not quite as popular from a facility standpoint. Again, it has that tank pressure is modified, and there's pumps associated with it, and temperature control and heat exchangers involved with those systems. Again, a booster pump has to be used to compress it to the pressures that are needed for the instrumentation in the lab. Nice thing is, in this case, you put the tank outside the building, so if you had a CO2 leak, it goes into the atmosphere versus inside a building where your ventilation has to remove it. Generally recommend with larger volumes that you also add CO2 or oxygen sensors into your laboratory. CO2 is preferable because those sensors will react immediately to the presence of CO2. And because CO2 is heavier than air, those are usually mounted near the ground in your location. Not going to spend a lot of time on this slide, but there's considerations to think about when you're actually connecting up the cylinders or dewars. It's important to make sure you have the right gaskets. You want to obviously leak check your connections. Nice to use valves to shut off valves in different places to help with that. You don't want high pressure venting in the lab when you're trying to change these out. There's various commercial grades of CO2 available. Obviously, the purer the material, the more expensive it is. You can buy what's termed a supercritical fluid grade purity material these days. Sometimes you can get by with lower purity grades depending on how you're utilizing your CO2, how you're actually bringing it into your instrumentation in the lab. If you pull the gas off the top of any dewar, that's actually one way of actually kind of further purifying cruder material. So some people will buy the lower grade material and then draw off the gas and recompress that to a liquid before pumping it into the CO2 system. As we've touched on a little bit, CO2 is very cold under pressure. Of course, dry ice you would have to handle with gloves, and even as a liquid, it's very cold. So gloves are recommended when you're working with the dewars or cylinders. You obviously need to be somewhere where you have high air turnover. So you want to make sure you have good ventilation. To the right of the slide, you can see the varying levels of CO2 where things become a concern above a certain level. Generally for CO2 sensor monitoring, set point's generally around 5,000 ppm, where you might start having issues. Below that, anything above 1,000, you might slowly start having problems with concentration, maybe a headache or feeling a little tired. However, the real danger point, you get above 30,000 ppm, that's where within 10 or 15 minutes, suffocation can be a real problem. So that's why we set the CO2 sensors much lower than that. You don't want to set them too low, otherwise you'll be tripping it off constantly, and none of us generally sit right by the cylinders or the CO2 doers, so that's why the 5,000 is sort of a good compromise for monitoring CO2. Also, you'll want to obviously wear safety glasses or even a face shield, depending on what you're doing with the CO2. So definitely, if you're setting up CO2 infrastructure, even with cylinders, you want to review this with your health and safety personnel. Also work with your facility and your gasifier engineers for optimal design if you're going with the bigger doers or the bulk system approach. And again, this is what's already done typically if you're any other gases you're using in your modern chemistry laboratory. Because CO2 is corrosive, like talked about earlier, the right type of piping is needed. 304 or 3/16 grade stainless steel is preferred. One can use copper, but especially for the larger systems, you'll want to use stainless steel piping. That does add some cost to your facility's build, but once it's there, you're good for many years. The booster pumps regulate the CO2 pressure, but you may also want to put a CO2 regulator next to an instrument, especially an analytical instrument, where you really need to fine-tune that pressure. Our prep systems don't care quite as much what the pressure is, and can make adjustments accordingly. Heat is built up at the booster as well, so that does heat the CO2 when you're pulling it out of a larger container. So either if you have a long run of piping, it'll cool toward ambient by the time it reaches your instrument, or you may have to add in some sort of heat exchanger to force that near the source of the booster pump. So a system like this one shown to the right, a VATRAN system, is used to pull the gas off the top of crude, or well, you can use it for any CO2 doer, recompress and bring it in, or there's liquid pumping type booster pumps as well available on the market. So in conclusion, even though the capital costs of setting up CO2 for higher volume systems can be daunting, can be as high or higher than the cost of the instrument initially, those will be offset by the environmental impact, return on investment, and your operational cost savings over time compared to the typical LC operation in this day and age. SFC has already become the preferred approach for chiral chromatography, especially in the pharmaceutical labs like I worked in previously before joining Teledyne. We were using it for 95% of our chiral chromatography in recent years. It's also become more readily used for achiral, and because there's a whole plethora of achiral stationary phases designed specifically for SFC use, that makes a screening approach and method development approach to that feasible, and you can easily run a lot of samples using this versus HPLC. And because systems are much easier to use, like our system, this day and age, it definitely belongs in most laboratories today. So these are some of the column chemistries that are generally used in flash and HPLC, and these are also readily available, and we also have some SFC column chemistries available that you can use with our instrument or anybody's instrument. There's a QR code up to the right if you want to get more information there. Also, more tools available on our Teledyne Labs website. Recommend that you poke around there. A lot of good information available there. Also like to advertise some upcoming webinars, one in December as well as January. So please register and tune into those. You'll hear more about prep SFC and people will go into more detail on the chromatography. I'd like to thank you for your attention and have a great day.
Well, thank you, Eric, for sharing your expertise. And I know there are a lot of questions that are being submitted. However, Eric would like to answer these by email. So he will be taking care of that shortly. Eric has shared our upcoming webinars, and we hope that you can join us for those. This webinar was recorded, and the video will be made available to you in the near future. So thank you again, and we hope to see you again next time.